Okay, so let's start lecture number 2 on us. Right, there's a little bit left from last lecture number 1. So first, we set up an exam time. If you go to the time edit schedule, I added May 31st as the exam date, 9 to 11. And August 19 is the re-exam date. So if you did not make the exam in May, you may choose to test in August. So the other schedules, the other classes are not entered in time edit because it's quite tedious. So you must enter each one manually by hand. And I think it's not necessary as long as you know the time is Monday, Wednesday. That should be okay. So I just added the 2 exam dates. So as I mentioned before, exam is open book, which means that you can look up anything, PowerPoint slides, any material online, and so on. So at exam start time, 9 o'clock, I'll send out the exam paper online in Canvas, and then you can start filling in the exam paper and submit it by 11, by the end of the exam time. So, are there any questions on exam or last lecture's material? Okay, so let's continue. We have one last section in introduction and overview, that is V2x. So V2x communication, in the 3GPP standard, there's 4 types. One is vehicle-to-vehicle communication, for example, collision avoidance system. One is a vehicle-to-pedestrian, V2P communication, for example, safety alerts to pedestrians and bicyclists. Specifically, it's a vehicle to mobile phone, mobile device. Vehicle to infrastructure, that's V2I communication. That is, for example, adaptive traffic light control, traffic light optimal speed advisory. So, for example, if there's a road, in one direction there's a lot of traffic, but in the other direction there's very little traffic. Then with the normal traffic light that switches lights periodically, the busy road will get interrupted periodically. But if you have V2I communication and change the lights only when the other direction has a vehicle coming, then you can be much more efficient. And speed advisory is when your vehicle can communicate with the traffic light at some distance away, and it can tell you that when it's going to turn green or red. And then especially for an automated vehicle, it can adjust its speed to fit the time when the traffic light changes. So vehicle to network communication, that is really vehicle to cloud. It's useful for real-time traffic routing. For example, if you the typical routing is based on shortest distance traveled between 2 points going through a given route. But if you can have real-time traffic information, then maybe Google Maps or some other mapping service can provide a shortest travel time, taking into account possible congestions on certain road segments. So that's the 4 types of V2x communication. So there are essentially 2 camps in V2x. One is based on Wi-Fi, which in IEEE standard is 8.2.11p, operating at 5.9 gigahertz. The standard is called DSRC, Distributed Short Range Communication, mainly adopted by Toyota and General Motors. Because it's a point-to-point communication without going through the base station, it's useful for latency-sensitive applications. Cellular V2x, CV2x, is mainly supported by Qualcomm and Ford and others. So traditionally, it's for latency-tolerant applications. For example, over-the-air updates. Updating your vehicle's software from over-the-air software patches. So these can be done non-real time, maybe while the car is parked. So traditionally, you think of CV2X as slower because the communication goes through a remote base station. So think of your own mobile phone. If your mobile phone is using cellular connection, then all the signals go through a remote base station in a cellular network. Whereas if you are in a room, you have Wi-Fi, then its communication is local. So CV2X used to be thought as being not suitable for latency-sensitive applications like collision avoidance, like V2V communication. But in recent years, as with the advent of 5G, CV2X will become more prevalent. It's also used for latency-sensitive applications. I'll discuss later in the slides that it has some modes of operation that's also independent of the base station. So in recent years, due to the popularity of 5G, CV2X seems to be winning over DSRC. So the following slides are based on the Qualcomm's CV2X approach. So in autonomous driving, V2X can have many applications. One is non-line of sight sensing, provides 360 degrees NLOS awareness, works at night and in bad weather conditions. So yeah, that's when you cannot see the other vehicle. So suppose this is your ego vehicle, and there's another vehicle. Maybe there's a tall building in the corner that prevents you from seeing that vehicle directly. Or maybe a pedestrian crosses the road suddenly. So they're called vulnerable road users. So if you have a V2X communication, then you can receive an alert, either V2V or V2P, and then either the driver or the automated vehicle itself can take emergency maneuvers. The other application is conveying intent. So shares intent, sensor data, and path planning information for higher level of predictability. So here, the blue car is your ego vehicle, and there's a road hazard, maybe some obstacle on the road that you cannot see directly, but your front, the car in front sees it, and it'll make a sudden lane change. So so if there's no V2x communication, then maybe you'll see it and you have to make a sudden lane change. So, but with V2V communication, the front vehicle can tell your own ego vehicle that there's an obstacle in front and you can change lanes early. Situational awareness offers increased electronic horizon to support the soft safety alerts and graduated warning. So here you may have congestion in front, many cars with reduced speed. So if you have V2V communication, they can send messages to your ego vehicle, and you can get a queue warning. So it's called a traffic shortwave. So in this case, you can either slow down or change to a different route. So V2x technology evolution. So it started with basic safety messages, basically collision avoidance over either Wi-Fi. So if you see this 8.2.11, that's Wi-Fi. That's just the attribute standard for Wi-Fi. Or CV2X release 14. And enhanced safety, that's a CV2X release 14/15, features enhanced range and reliability. So, so the range is extended to maybe over 100 meters and more reliable. And then release 16 offers advanced safety, offers higher throughput, higher reliability, wideband ranging and positioning, and lower latency. So this is essentially 5G. So in last year, July, the 3GPP, the third generation partnership project, that's essentially a consortium of industry, telecom industry, technology companies. They declared release 16 to be frozen, finalized. So this is a table comparing release 12.13 to 14 up to 16. So release 12.13 is for a basic device-to-device communication. So it has limited network independence, limited high speed, no high density, and so on. Enhanced safety, release 14.15. It has it has high speed support, high density support, high throughput, low latency, high reliability, and the shared positioning information. And release 16, 5G new radio support, NR support. It has ultra reliability, low latency, high throughput communication, suitable for autonomous driving. So 5G is a large standard. It's designed for essentially one part of 5G deals with high bandwidth communication for consumer devices. For example, you can download a large movie in a few seconds. The other part deals with safety critical real-time communication. So that's the part that concerns autonomous driving. So CV2X, cellular CV2X defines two transmission modes. One is the more traditional CV2X cellular. It's network communications going through a base station. So here's the base station. in telecom jargon is called E node B, and the device, the vehicle, communicates with the base station and going through the base station to the other vehicles. The interface is called UU interface. And the other, more suitable for real-time communication, is V2x direct. So it's device-to-device direct communication without going through the base station. So here you can see in the picture, you have two vehicles, one pedestrian with a mobile device, and one roadside unit, maybe a traffic light or some other roadside unit. And these four devices can communicate directly without the base station. It's called the PC5 interface, operating on 5.9 gigahertz, independent of the cellular network. So this direct communication is pretty much similar to Wi-Fi, and it's what makes CV2X suitable for real-time scenarios. So the drawback, of course, is limited range. Whereas for the network communication, V2X cellular, the range is essentially unlimited. So here are use cases for latency tolerant applications. For example, discovering parking and charging stations, cloud-based sensor sharing. So vehicles can share information on traffic light status, for example, over a long distance, traffic flow control, queue warning. So if there's congestion ahead, maybe a few kilometers ahead, you can get a warning very early. Road hazard warning 1 kilometer ahead. So maybe there's a sharp turn in this road segment, and you can get, if the car breaks down, you can get, if the road is very slippery, so this front vehicle can send a message going through the base station to a later vehicle very far away, so to give him a ahead of time warning. So these are latency tolerance use cases. So latency is not critical in these scenarios. And then for latency sensitive use cases, mainly for active safety, so it can be useful for non-of-sight scenarios. So here, this is your ego vehicle, and this is a two-lane road, and you want to pass the front vehicle. But in the other direction, there's a car coming. So if you cannot see the other car, it's very dangerous. So do not pass warning can be useful in this case. So this is intersection movement assist. So this is when there's tall buildings in the city. Here, tall buildings, so you cannot see around the corner. And then you can get a warning that there's other car in the other direction. There may be other vehicles coming, or some emergency vehicle that you must yield to. So there's a blind curve local hazard warning. So this is a curved road, and a car breaks down here, and it can send a message to other vehicles. And vulnerable road user alerts at a blind intersection. So here, a vulnerable road user may emerge from some other parked vehicle or from other obstacle. And this is a very common, very dangerous situation. I'm sure if you drive, you know this situation. Some children often run out from parked vehicles, and it's very hard to predict. So if you had a V2P communication, then the mobile device on the person can send a message and give a warning. A roadworks warning. So here you have a construction site on the road, and you have a large truck in front. And then the truck swerves to avoid the construction worker, and you may not see it directly, but you may get a warning from the truck in front. And left turn assist. So it warns you of oncoming. Maybe you want to turn left, and maybe you are focused on the vehicle in front, but there's a car coming on the right, from the right at a very fast speed. And then this left turn assist can give you a warning. So all of these are non-line of sight scenarios. So for deployment, it's a combined use of roadside units. For example, traffic lights. These are traffic lights, and this is with direct link interface for V2x direct. So this purple interface is the roadside units with direct link, also called PC5 interface. So it allows direct communication between the vehicle and the roadside unit. So between this and this. And 4G, 5G base stations for V2x cellular, benefiting from cellular network densification in 5G with smaller and denser cells. So the green interface is the 4G, 5G small cells with UU interface. So that's more of a traditional base station, pretty tall, on a tall pole. And then in 5G, you may have so-called nano base stations, very small base stations spread densely in the area. So the prominent feature of 5G is that the cellular the cells in the cellular network must be very small, because the transmission range is very short. So you're forced to set up many small base stations as opposed to a few large base stations in 4G. It's said that you may even have furnitures embedded with 5G base stations to enhance the signals, enhance communication signals. So in 5G, a prominent feature is smaller and denser cells. So with the smaller base stations, you can also communicate. For example, this vehicle with the UU interface, the green interface, can communicate with other vehicles going through the base station. So that's the two types of communication. One is direct communication, one is network communication going through base stations. So here's a use case for a disabled vehicle after blind curve. So here's a vehicle disabled on the road, and here are vehicles coming, turning a blind curve. So CV2X has at least 2 times longer range than the SRC standard, which enables the ego vehicle to get warning message earlier, hence travel at higher speed while avoiding collision with the disabled vehicle. So this picture essentially shows for the 2 different standards. For the older DSRC standard, it has 60 meters range, communication range, whereas for CV2X has 107 meters range. And then for normal road condition, versus for icy road conditions. And for each combination, you can work out the safe velocity for the vehicle. So, for example, at this point, normal road condition CV2X, you can divide the stopping distance by the velocity and get based on the driver reaction time and braking distance, you can get the safe traveling speed. So the overall conclusion is that with a longer range communication, obviously you get the warning earlier and the vehicle or the driver can respond earlier. Therefore, you can travel at a higher safe speed. So the other use case is do not pass warning. So CV2X longer range enables the ego vehicle to get warning messages early, hence travel at a higher speed. So for example, this vehicle, your ego vehicle wants to pass the truck in front, but there's another vehicle coming from the right. And there's a distance of 443 meters between you and the other vehicle. So with CV2X, with longer range communication, you can travel at a higher speed while maintaining safety. So 5G AA is a cross-industry consortium that defines the 5G V2X communications for essentially autonomous driving. It's called 5G Automotive Association. It includes the automotive companies and also the telecom companies. So in conclusion, in summary, 5G accelerates AVs. So for autonomous vehicles, you can have V2X wireless communication as an additional sensor. So it can be viewed as additional sensor in addition to a camera and LiDAR and radar. And you may have 3D HD maps with V2 cloud connectivity. You may have heterogeneous connectivity with cellular Wi-Fi and in-vehicle CAN Ethernet, and enables onboard intelligence. So my thoughts on 5G is that for AVs, to benefit from V2X, you need massive deployment of V2X. That is, if only one vehicle is equipped with V2V communication, obviously it's not useful at all. You need many vehicles with V2V communication to be useful. So up to now, it's a very promising technology. There are many test beds that demonstrate the usefulness of V2X, but current AV players are not counting on V2X. So, so current automated vehicles from Waymo or Tesla or pretty much any other company are single car intelligence systems. They do not rely on V2X. Obviously, if you have V2X, they can use it, but their operation do not depend on the availability of V2X. Okay, so that's a short section on V2X communication. Any questions? Okay, so let's close this first lecture and move to the lecture 2 on functional safety. So this lecture, I took a lot of material from Audacity's self-driving car engineer nano degree. So let me do a little advertisement because I use their material. Audacity has this nanodegree program for self-driving cars. It's not free. It's actually quite expensive, $2,000. So it's pretty well known in industry. So if your goal is to become a self-driving car engineer, this course can be very useful because many employers know it. They often ask applicants, did you take the course or not? So because so many people took it and got a job, so this course is pretty well known in industry. So from my perspective, so I looked at the course material, and it's very practical, very hands-on, but it's also a little bit out of date. So it addresses many classic techniques in terms of vision, computer vision, sensor fusion, planning, control, and so on. But it lacks adequate coverage of machine learning and deep learning, the latest topics. So if you're aiming to get a lot of practical knowledge to learn about how engineers what they really do in industry, so this course can be very useful. But if you're a PhD student or doing research, maybe these covered topics are too old. So the link is on the first slide. So the outline of this lecture is first introduction to functional safety, and then hazard analysis and risk assessment, HARA, and then functional safety concept, technical safety concept, finally functional safety for hardware and software. It follows the development flow. So some basic vocabulary. A fault is when something inappropriate happens to the system, such as a defect or unexpected behavior. So a fault can lead to a failure, which is synonymous with a malfunction. Failure means that the system has stopped working properly and is no longer doing what it's supposed to do. So a failure can lead to a hazard, which is a situation that could cause injury to a person or harm a person's health. If a system fails, the situation is potentially hazardous. So hazards can have different levels of risk. So for example, if a resistor in your car radio hardware breaks, so that's a fault, and the radio won't turn on. So that's a failure, a manifestation to the user. And then you won't get to listen to music. But that failure won't cause you bodily injury or harm. So it's a hazard with a low risk. So it is a hazard. I mean, it annoys you because you cannot listen to music. But this hazard is not a serious hazard. So the other example is if a resistor in the power steering hardware breaks, that's a fault, and the power steering system could fail. That's a failure. So if you are driving at a high speed, then you might get injured quite badly. So this is a hazard with high risk. So the notions of safety in the automotive context, there are many notions. One is functional safety, which is the topic of this lecture. It's when hardware, software not working according to specification. One is safety of intended functionality, SOTIF. That's a hazardous situation due to lack of specification. So functional safety is more related to traditional hardware-software failures. So if a resistor is broken or there's a soft error due to the failing aging hardware, whereas the SOTIF is more relevant to AI and machine learning. So for example, if Tesla's car cannot recognize a white truck and hits it, so that's a failure in the SOTIF sense, because the hardware in the car did not fail. It's the function that's not working properly for a given input. So I will mainly discuss functional safety in this lecture, but I'll also briefly mention SOTIF in the end, because SOTIF is relatively new, whereas functional safety is very old, way before autonomous driving. But SOTIF was discussed to respond to the new requirements due to autonomous driving. The other issues are safety in use, hazardous misuse, misunderstanding, active passive safety. So passive safety mechanisms are like seatbelts, and airbags. Active safety mechanisms are the maybe emergency automatic emergency braking and so on. And security, obviously, it affects the safety. If someone hacks your car, it can cause a safety violations. So security has a separate standard in the automotive context. So functional safety comes from a branch of systems engineering called requirements engineering. It separates requirements into functional requirements and non-functional requirements. So functional requirements says what your system is supposed to do. So that is the function with the form X system shall do Y. So you see the word shall a lot in the functional safety literature. So the turn signal system shall turn on an indicator light telling the driver that the system is active. So that's one example of a functional requirement. Whereas a non-functional requirement addresses how the system should behave. For example, how reliable is the system? With the form X, system shall be something. So for example, the turn signal system shall be available when the vehicle ignition switch is in the on position. So it doesn't specify the function of the turn signal system. It only specifies its availability at a given time. So it's not a functional requirement, but a non-functional one. So functional safety looks at what happens when the system does something that it was not supposed to do, which is called a malfunction. So you'll be adding new engineering requirements to the vehicle design in order to ensure safe systems. So automotive functional safety is only concerned with electronic system malfunctions. So it's just one part of overall vehicle safety. So vehicles have a number of different systems, including EE system, hydraulic, mechanical, and chemical. So there are a variety of other automotive standards covering the topics about safety that's not about the EE system. So for EE system, is the functional safety. So functional safety does not look at nominal performance. Nominal performance issues can lead to safety problems, but nominal performance is not a part of the functional safety standard. For example, nominal performance of the automatic braking system could be a vehicle traveling at 60 miles per hour should come to a complete stop in 5 seconds, whereas functional safety does not determine whether or not the vehicle brakes within 5 seconds. It looks at malfunctions, such as if the braking function is not engaged when it's supposed to, or if the braking function is engaged when it's not supposed to, or if the system is braking too hard, causing injury to the driver. It's not about the quantitative performance, but about malfunctions, something that doesn't work. So here's a quiz. Which of the following is part of a functional safety analysis? First is the mechanical seatbelt restraint system could fail and the passenger would be injured in an accident. Second is testing to see if the backup camera actually meets its technical specifications of a depth perception of 20 feet, and so on. So the answer is number 3. There's a potential that a software error could cause the parking brake to engage at high speeds. So it's a malfunction of the EE system. Whereas for the first one, it's a malfunction of a mechanical system. For the second one, it's a performance specification of the camera system. Camera system is part of the EE system, but this particular statement addresses the performance, not the malfunction. Number 4, the car battery might catch on fire because of a chemical reaction. So it's a chemical subsystem, not the EE subsystem. So functional safety analysis, so safety is defined as absence of unreasonable risk. So functional safety analysis identify high-risk situations, lower risk to reasonable levels. So it has 3 steps. One is identify hazards in the passenger vehicle's EE system that could cause physical injury or damage to a person's health, and evaluate the risk of the hazardous situation so that we know how much we need to lower the risk. And finally, via systems engineering, prevent accidents from occurring by lowering risk to reasonable levels. So what level of risk is reasonable? So it really depends on the society's current threshold. For example, the history of seatbelts provides a great example of how society measures risks. It took almost a century for countries to require seatbelt use. So it was the automobile was invented in 1885 by Benz, and seatbelts started appearing in 1920s, and 1950s, the car companies offered seatbelts as optional equipment. And finally, in 1968, United States passed laws requiring all vehicles to come with safety belts. And 1984, there's a few other milestones. So today, all vehicles come with seatbelts, and you must wear a seatbelt while in the vehicle. So by the measure of contemporary society, driving without a seatbelt is an unreasonable risk. But in the past, driving without a seatbelt was considered reasonable by society's standards. So perhaps one reason is that vehicle speeds are much faster today. The other is that people have a lower threshold for tolerance of potential risk. So typically seatbelts are mechanical systems, so they're not part of the functional safety coverage, but some parts of the seatbelts may be electronic, so they should be considered as part of functional safety. So identifying hazards. So there are three general causes for accidents. One is human error. The United States Highway Administration estimates 94% of car accidents in the USA involve human error. One is technology error, for example, software bugs, hardware failures, and so on. A human technology interaction error. So whenever a human and a machine share control of a vehicle, of a system, extra care must be taken when evaluating safety. The boundary between what the human is supposed to do and what the machine is supposed to do needs to be clear. Drivers need to understand the warning signals coming from ADAS systems. Interfaces need to make it clear when the vehicle expects us to take over. Some companies, such as Waymo, has argued that low levels of automation are not safe. Hence, it's unrealistic to expect drivers to keep their hands on the steering wheel and be prepared to take over for long durations of time. So, for example, Tesla has L2 automation, and in their user's manual, they say that the driver must be alert and be ready to take over at any time. In fact, many drivers overtrust the technology, and that's the cause for quite a few fatality accidents before for Tesla vehicles. And it's very hard to pay attention when the vehicle appears to be working so well for most of the time. So then you relax and you tend to overtrust the technology. And human attention, it's very hard to bring your attention to driving in a very short time. So Waymo has argued that that's essentially a dead end. You cannot expect humans to be alert at all the time. So that's why they're starting from L4, L3, L4, and in fact, they had at a certain period of time, they were designing a vehicle without steering wheels, but I think they gave up later. So, but their overall philosophy is that you should start from a high level of automation. High levels of automation will remove hazards due to human technology interactions. So here's another quiz. Classify the causes for the following. One is software bug causes the vehicle to accelerate inadvertently. That's a technology error. Second is the driver goes too fast around the curve and falls off the road. That's a human error. And finally, a radar-based vehicle detection system is too sensitive and buzzes even when a crash is not imminent. So the driver ignores the warnings, which could lead to an accident if the crash were imminent. So that's a human technology interaction error, or also called human machine interaction error. So the ISO 26262 standard, which is the functional safety standard for automotive systems, defines 4 ASILs, automotive safety integrity levels, A to D. So D represents a hazardous situation with the highest risk, whereas A represents lower risk. There's one more level of risk below A called QM, quality managed, which means that development of this subsystem according to accepted quality principles is sufficient to reduce risk. So that is the automotive manufacturer can handle the development of QM without any safety certification requirement. So QM is not covered by ISO 26262, is covered by another standard. So ASILs are determined by HARA, a hazard analysis and risk assessment. So how do you evaluate risk? It's defined in the functional safety context as probability of occurrence times severity of the harm. So probability of occurrence refers to how often a driving situation occurs. For example, driving on a snowy mountainside road, that has a relatively low probability of occurrence. Whereas for city driving, the probability is high. Well, unless you live in the mountains, but I guess most of us live in the cities. So severity of harm refers to how bad the injury is. For example, a power steering malfunction may cause fatal injury for driving on a snowy mountainside with a severity of 4, but unlikely with no injury for city driving with a severity of 2 due to the low speed. So therefore, risk of power steering malfunction for driving on a snowy mountainside is calculated as 2 times 4, which is 8. So you can look at a few examples, probability of occurrence from the very low to very high. Very low is when a vehicle jump start needed, when you run out of battery. Very high is when you're driving on the highway. Severity from no injury to light and moderate injury up to life-threatening injuries, fatal injury, and you can calculate the risks for the following. So while driving on the highway, brakes fail at high speed. So and then driving on the highway has a probability of occurrence of 4 and severity of 4. So you have 16, very high risk. B, your vehicle requires a jump start. The power steering is not working, but the vehicle is parked on the side of the road and not moving. Then probability is 1, severity is 1, no injury. And the risk is very low. Similarly, for driving in the snow in the city, probability of 2, and anti-lock brakes fail, probability while driving at a low speed. And finally, driving at night on the street with no street lamps, the car headlamps fail. So for each one, you can get the severity and probability of occurrence. So reducing risk with systems engineering. So this is the V model for systems engineering from requirements engineering on the on this side, and the systems architecture design, allocating requirements, and testing and verification, and finally system integration. So this is a classic V cycle, especially if you work in the automotive industry. As an engineer, you should be very familiar with this V cycle. So the top part of the V represents the entire vehicle as a single system. As you traverse down the left side, you focus on smaller and smaller subsystems. As you go up on the right side, you integrate your subsystems into larger systems. So at the top left, you start from a bird's eye view of your entire vehicle and gradually split into subsystems such as climate control, entertainment system, steering system, braking system, and so on. Then you define requirements and system architecture for each subsystem, and then you focus on each a single subsystem. For example, the climate control system, and break down the climate control system into its subsystems, like the electronic control unit, the temperature sensor, the fan, the air filter, and so on. And then design the requirements and architecture for each subsystem, and For the left side and right side of the V, you can connect at a high level, that is at the system. After system integration, you check, you compare the results to design requirements to see if the design requirements are fulfilled. And at the subsystem level, you can also check that the implemented subsystem satisfies the subsystem requirements. So this is the ISO 26262 standard document. It's quite a lengthy document, and it's not free. You need to actually cost money to download. So it has these sections. Chapter 1 is vocabulary, 2 is management of functional safety, 3 is concept phase, 4 is the product development at the system level. And this is the V cycle. Each document concerns different stages of the V cycle. And there's a double V, W here, which I'll discuss later. So that's the little V cycle for the hardware development. That's the little V cycle for the software development. And then you have other documents for supporting processes and ASIL-oriented and safety-oriented analysis. So I will go through the top parts, but not the miscellaneous parts in the bottom. So here's the another view of the V model. So ISO, this standard compliance is not legally required, but highly desirable. So higher up in the V model represents integrated systems. So you have the flat down, flat up, and flat shape. And lower down in the V cycle, you have 2 small basins. So left small basin for hardware development, right small basin for software development. And the downward arrows on the left side of each basin represent the requirements and design. And upper arrows on the right-hand side represent prototyping, testing, and integration. So you can flatten the V model to a more linear perspective. So here you can see the concept phase, product development phase, and after release for production phase. So the concept phase, you mainly perform HARA, hazard analysis, and then you design the functional safety concept. And then after the requirements are done, you perform actual development at the product development phase, both for hardware and software. And then you perform safety validation and functional safety assessment and release to production. And finally, after production, you have the operation and service and decommissioning, that is going to a junkyard. So this figure shows the development process. Essentially, it's a stepwise refinement process. So you first perform a HARA to identify the safety goals for each item, and then you derive functional safety requirements for each safety goal, and allocate FSRs to architectural elements to perform preliminary architecture and system architectural design. So allocate functional requirements to each of the elements in the architecture, and then you refine it to actual hardware elements and software elements, which and then you allocate the technical safety concept, the requirements onto the more detailed system architecture design. so essentially, it's at different levels of abstraction. At a higher level of abstraction, you're allocating the FSR's functional safety requirements to more abstract architecture elements. And then at a lower level, you're allocating the more detailed technical safety requirements to the more detailed hardware elements in the system architecture. So before we go into HARA, the next section, I think it's time for a little break. So today, everyone is very quiet. There's no questions. So let's take a 10-minute break. Okay, hope everyone is back. Let's go into the next section on HARA. So HARA, this is where we brainstorm and imagine hazards where the system malfunctions and causes injury or harm. So then you calculate the risk for each hazardous scenario. So it has 5 steps. One is situational awareness. Choose the driving scenario, like driving on a bumpy road, being towed, and driving on a freeway. Hazard identification, identify how the system could malfunction. For example, electronic parking brake failure. Hazardous event classification according to exposure, severity, and controllability. So take a malfunction and think about the malfunction under different driving scenarios. Like if the electronic parking brake failed while the vehicle was parked on a steep hill. So that could be a hazard. Then calculate the 3 metrics, exposure, severity, and controllability, and determine the ASIL. ASIL determination. Finally, safety goal. The type of engineering requirement for vehicle functional safety. For example, the electronic parking brake system shall always be engaged when the vehicle is in park on a gradient that's greater than 10 degrees. So, so first, some basic terminology. An item is a high-level system in the vehicle. A system is a set of elements that have at least a sensor, controller, and an actuator. For example, the lane assist system, LAS, has 2 sensors. One is the camera, one is the driver steering torque sensor. The ECUs are the controllers, and actuator is the motor that turns the steering wheel. A subsystem is a smaller piece of a system. A component, maybe an ECU, an embedded computer that contains the hardware and software for specific functionality. A component consists of hardware parts and software units. So here's an example lane assistance system with 2 functions. One is lane departure warning, one is lane keeping assistance. So if a driver departs a lane without using a turn signal, the system assumes that the driver has become distracted and did not mean to leave the lane. 2 things will happen. First, the LDW's function will vibrate the steering wheel to provide a driver haptic feedback to give him a reminder that, hey, you're deviating from a lane. The LKA function will move the steering wheel so that the wheels turn towards the center of the lane in order to stay in eagle lane. So LKA is more active. It's an active safety feature. So you can assume that these requirements, this engineering requirements come from a product engineering team, and the safety engineer's job is to add extra requirements to ensure safety. So here's the Ers architecture. You have a one item. The overall system is the green box is the item. So that's the E system item. And then the steering wheel is a mechanical component. So within the item, you have one system, the red box, and 4 subsystems, the blue boxes. So subsystems may be nested. For example, electronic power steering ECU is a subsystem that's within a larger subsystem, which includes the sensor and the actuator. So situational analysis, this is where engineers brainstorm about hypothetical driving situations and analyze what would happen in case of vehicle malfunction. For example, brake failure, control unit short circuit, bib flip, airbag deploys unexpectedly, and so on. So you use a set of predefined guide words to help unify terminology. So here, deviation, a guide word includes a function not activated, function unexpectedly activated, function always activated, and so on. So, so for example, operational mode on operational scenario during environmental details with situational details and item usage system. You can replace each item, each word in the parentheses with, say, backward driving on city road. So backward driving is operational mode. City road is a scenario. And during fog is environmental details. And situational details are low speed. And item usage is correctly used system. So that's one scenario. For our lane assistance example, is a normal driving on a highway during rain, slippery road with high speed and correctly used system. So the function for LDW is that it should apply an oscillating steering torque to provide the driver haptic feedback. So if you have this function in your car, you know, if you deviate from your lane, your steering wheel will vibrate and remind the driver. So malfunction is that the actual effect is too much. That is, when the oscillating torque is too high, then the oscillation can actually cause the vehicle to veer and collide with other vehicle. So the details are that the haptic feedback is too large, can affect the driver's ability to steer as intended. So he could lose control of the vehicle and collide with another vehicle or with road infrastructure. So summary is that LDW applies too high an oscillating torque to the steering wheel above limit. So this is a hazard. So for lane keeping assistance, this function moves the steering wheel so that the wheels turn towards the center of the lane to keep the vehicle in the lane. Malfunction is when the driver takes both hands off the wheel. So that's when the driver overtrusts the technology. And LKA is not designed for that. It's designed for assisting the driver, not replace the driver. The driver incorrectly treating the car as an AV, causing LKA to be always activated. So that's a malfunction. Hazardous event is collision with other vehicles. So in the ISO 262 standard, the risk is defined as risk equals severity times exposure times controllability. So severity is the same as the severity we discussed before. So exposure corresponds to probability of occurrence. The controllability is new in the ISO 262 compared to traditional functional safety. It measures how likely the driver could gain control of the vehicle. So probability of loss is exposure times controllability. So in the table here, we see a probability of loss is determined by exposure and controllability. Exposure has incredible to a high probability, and controllability could be controllable in general up to a difficult to control or uncontrollable. Severity ranging from no injuries to life-threatening. So for example, normal driving on a highway during rain, slippery road with high speed and correctly used system. severity is 3, S3, because highway driving implies high severity of harm. And exposure is E3, medium probability. So it's not uncommon, but also not every day. And controllability is C3. A driver may lose control if the steering wheel vibration is excessive. And then you determine the ASO level of the LDW function as ASO C, because there's a table in the standard, S3, C3, and E3. So it's a three-dimensional table displayed in a flat 2D manner. So you can look up the ASO level to be C. So obviously, higher the each of the axes, if the higher severity, higher exposure, higher C controllability, the number is higher means that it's getting more difficult to control. Each one axis, when it grows larger, grows higher, then you're more likely to have a high ASO level. So you may look at other driving scenarios. For example, driving on a wet road on a city street at low speed. Now you can determine severity as pretty low. Exposure is medium, and controllability is C3. You may lose control. But because the severity is low, the ASO level, you can check the table, is A. So therefore, the risk has gone down due to the low speed. Driving on a dry road on a city street at low speed, now you have severity is S1, exposure is E4, because you have no rain on most days. So dry road is more likely than a wet road. And controllability is C3, same as before. Then if you look in the table, you have ASO-B. Mainly due to a higher exposure. So there's a higher probability that a random malfunction will occur on a dry road, hence risk increases for the dry road scenario. Finally, you have driving on a dry road on the highway at high speed. Now you have severity as S3 because it's high speed. Exposure is E4, very common. Controllability same as before, C3. So you have ASO-D. Now this function is very safety critical because it can cause a severe harm. So when more than one situation maps to the same hazard, then choose the highest ASO level for it. So for example, if you want to determine LDW functions ASO level for city driving, regardless of wet or dry road, then you take the maximum of ASO-A for wet road and ASO-B for dry road to get ASO-B. So it's important to notice that ASO is not equivalent to importance. So a high ASO function is not necessarily more important than a low ASO function. And also importance is not even a formally defined concept in the standard. So consider two safety functions. Safety function 1 is ASO-C due to severity 2, exposure 4, and controllability 3. And system function 2 is ASO-B due to severity 3, exposure 2, and controllability 3. So SF2 is assigned a lower ASO of B due to its low exposure, but its severity is higher than SF1's. So malfunction of SF2 may cause more severe harm than malfunction of SF1, but because it's less frequent, exposure is lower, then it gets assigned a lower ASO than SF1. So a low ASO function may be very safety critical. So in general, higher ASO levels require more analysis and testing to reduce risk to acceptable levels. So a few examples of extra measures include fault tree analysis for ASIL C and D, and ASIL D requires hardware failure rate of less than 10 FIT, which is number of failures expected in 1 billion hours of operation. ASIL B and C require 100, and ASIL A requires 1,000. So software units with ASIL D require more rigorous testing, like MC-DC coverage, whereas ASIL B only mandates DC coverage. So safety goal for the LDW function, for the hazardous event that LDW function applies too much an oscillating torque to the steering wheel, the safety goal is that the oscillating torque from the LDW function shall be limited. This goal eliminates that hazard. So what's the safety goal for LKA function? So answer is 4. Lane keeping assistance should be time limited, and the additional steering torque shall end after a given time interval so that the driver cannot misuse the system for autonomous driving. So here's a summary of HARA. You start from the malfunction, that is the ABS system failure. Then you perform hazard analysis to identify what unintended situations could happen. For example, a loss of stability. Risk analysis, how likely is the hazard to happen? That is the exposure. How harmful is the hazard, the severity of the hazard? How controllable is the system if the hazard occurs? That's controllability. Finally, you determine the ASIL based on the risk analysis from A to D. There are a lot of specific methods for the failure analysis, which I do not go into the details. So that's a HARA, and then the next step is a functional safety concept. So in the standard, concept is synonymous with document. So it includes the following steps: derive functional safety requirements, refine the item architecture, allocate functional safety requirements to item architecture, and determine ASILs for the subsystems. So based on information from HARA, we identify 2 malfunctions for LDW. First, the LDW function applies an oscillating torque with very high torque amplitude above limit. Second, it applies the torque with a very high frequency, also above limit. And one malfunction for the LKA function is not limited in time duration, which leads to misuse as an AD function. So, and then you can perform a safety analysis to derive safety requirements, identify conditions and causes that could lead to requirements violations, and identify other hazards not identified in HARA. They include the failure mode effects analysis, FMEA, and HAZOPS and FMEDA, FTA, and so on. So these are all commonly used in industry for safety analysis. But we'll just use some basic logic to derive requirements from the goals in this lecture. So functional safety requirements based on the 2 goals we identified before. First is that the oscillating steering torque from the LDW function shall be limited. Second is that LKA function shall be time limited, which means that the additional steering torque shall end after a given time interval so that the driver cannot misuse the system for AD. Based on these 2 goals, we derive a few functional safety requirements. First, the lane assistance item shall ensure that the lane departure oscillating torque amplitude is below max torque amplitude, and frequency should be below max torque frequency. So this is more specific than the safety goals. You explicitly define a threshold for amplitude and frequency. So that constitutes safety requirements. And then from the safety goal 2, you can identify a requirement that the lane assistance item shall ensure that the lane keeping assistance torque is applied for only max duration. Again, you have a concrete threshold. So after you have the 3 requirements, you allocate them to subsystems. So in this specific case, you allocate the 3 requirements onto this electronic power steering ECU. So it shall ensure that the lane departure oscillating torque amplitude is below the max torque, frequency is below max frequency, and lane keeping assistance torque is applied for no more than max duration. So you make a table of which requirement ID, requirement detail is mapped to which element. Could be mapped, in this case, it's mapped to the ECU. You may also have other requirements mapped to camera ECU, display ECU, and so on. So to implement the requirements, we add software blocks to the 3 ECUs. One is the electronic power steering ECU, one is the camera sensor ECU, one is the car display ECU. And the blocks inside the ECU blocks are the software blocks. So for example, here in the electronic power steering ECU, you have lane assistance functionality, analyze driver steering torque, and final electronic power steering torque output, the 3 components. You may also implement some requirements with mechanical components. So the 2 functional safety requirements inherit SOC from the safety goal. So we determined that this particular goal is SOC from exposure severity and so on. Now derived from this safety goal, you have the 2 requirements. They also inherit SOC from the goal. And then you allocate Acl to the specific subsystems. So the entire power steering subsystem, this red box here, inherits SOC from the 2 functional safety requirements, because this subsystem the functional safety requirement is mapped to the subsystem. It inherits the ASIL level from the requirements. Because in these 2 subsystems, camera and display subsystems, no functional safety requirements are mapped to them. So they're not required they're not relevant to safety analysis. So they can be assigned QM, the lowest level. So Acl decomposition can be used to lower the Acl level. For example, Acl D subsystem can be decomposed into 2 redundant Acl B subsystems. For example, if each Acl B subsystem has probability of malfunction as 0.01, then the overall system has probability of malfunction when both subsystems malfunction, right? Because they're redundant. When either one subsystem works, the whole system works. Only when both fail, then the whole system fails. Therefore, the failure probability of the overall system is probability of both failing at the same time, which is 0.0001, which is much lower, assuming independent failure modes. So that's the reason why you can decompose a high ASIL system into lower ASIL subsystems. It's also a motivation for sensor fusion. For example, if you're doing fusion of camera and LiDAR, and maybe if you're driving at night and your headlight malfunctions, then the camera is no longer working, but the LiDAR still provides you with information. So that's also an example of decomposition into subsystems. So in this case, the subsystems are labeled as ASIL B parentheses D. So in parentheses is the parent ASIL before decomposition. So here's the table from the document, from the standard document. So ASIL D system before decomposition can be decomposed into a D plus QM, or C plus A, or D plus B, B plus B. And similarly for ASIL C, B, and A. So for ASIL A, you can no longer decompose it any further. You can only be A plus A. So this decomposition can help reduce the certification effort for your system, because if you want to certify a system at an ASIL D level, it's very time consuming, very difficult. You need to provide evidence that your system fails at a very rare rate. But if you can decompose it into two ASIL B subsystems, then certification of each one is much simpler, much faster. So here's the ASIL decomposition for our example. We decompose the software block lane assistance function, which is ASIL C, into two software blocks. One is QM. So this one ASIL C software block is decomposed into this normal lane assistance function and safety lane assistance function to limit the torque. So this one is a QM, and this one is ASIL C. So the idea is that you have a normal lane assistance functionality which may output a torque that's too high. It's unsafe. However, you can add a kind of a guard system, this safety lane assistance functionality, limit torque, to limit the output torque from the normal system. So because its job is very simple, it's just everything else. If the torque exceeds the threshold, reduce the torque to the threshold. So the function is very simple. Therefore, you can certify this decomposed ASIL C subsystem very easily. And then you can be very relaxed on the normal lane assistance functionality, which is QM, because you know that there's another safety system guarding your output. So this significantly reduces the burden of system design and analysis at ASIL C level, reducing the scope of the certification of ASIL C. So from a real-time timing perspective, this fault tolerance time interval refers to the time it takes to detect and react to a malfunction. For example, for the requirement 1, the lane departure oscillating torque amplitude is below a max torque amplitude threshold. The fault is when the torque amplitude exceeds the threshold. And the safety state must be reached after a time interval FTTI, which is equal to a diagnostic test interval to detect the fault, and for the reaction time to react to the fault. So FTTI should not exceed the time until accident could happen, could say 50 milliseconds. It obviously depends on the car's speed. So the warning and degradation concept is a document that discusses how the driver will be warned of a malfunction and what the system will do to degrade the functionality, to take the system to a safe state and recover from a safe state. So gradual degradation versus turning the system off. So for these two functions, LDW and RKA, they're not critical, so we can turn them off. But some systems can provide limited functionality and degrade to different levels depending on how bad the situation is. For example, a car engine control system. If one sensor fails, the system may reduce the torque output of the motor so that the vehicle can still be driven but at a lower speed. So this helps the driver avoid getting stranded. So in case of malfunctions, you may turn on the warning light to give a driver warning. This is done by adding a separate software block, lane assist malfunction warning here, and a connection of safety lane functionality to it. So this concerns the display subsystem. So here's the overall workflow. You start from the item definition, and then you perform HARA to identify the item's ASIL level. Then you determine the safety goals, and finally you derive the functional safety requirements, FSRs, from each safety goal, and assign ASIL to it, and allocation to subsystems, and it has attributes such as fault tolerant time interval, a driver warning, degradation, safe state, and so on. So it's a step-by-step process. So after we have finished with the functional safety concept, the next document describes the technical safety concept. So that's when the concept phase is finished and the product development phase starts. So that's when you actually go into the development of hardware and software. So this concept involves two steps. One is turning functional safety requirements into technical safety requirements for each of the subsystems, camera, display, and power steering, and allocating technical safety requirements to the system architecture. So the technical safety requirement in this simple example, the only safety relevant element is the electronic power steering ECU. The other two, display and camera sensor, are not involved. So our technical safety concept will go directly to the ECU level. But in general, you may develop multiple technical safety concepts, one for each safety relevant subsystem. So the figure shows how a technical safety concept may be divided into several documents for each subsystem. So the functional safety requirement we discussed before is abstract and high level. So for example, the lane keeping item shall ensure that the lane departure oscillating torque amplitude is below a threshold, whereas the technical safety requirement is more concrete and describes the signal flow and which component is in charge of the functionality. So the LDW safety component shall ensure that the amplitude of the LDW torque request sent to the final torque component is below max torque amplitude. So this can be implemented by setting the LDW torque request to 0 if it exceeds max torque amplitude. But we're not concerned with implementation yet. So here's the software components. This is the QM level normal lane assistance functionality. This is the small safety check. We are trying to prevent the torque to exceed the threshold. So this smaller component, that is the LDW safety component, shall ensure the amplitude is below the max amplitude. So this can be implemented by setting it to 0 if it exceeds a threshold, but we're not doing that yet. We're just specifying requirements. So this little component here, SOC component, shall ensure that whatever the torque output from the normal functionality, the QM component is, it must ensure that the output to the actual hardware must not exceed a threshold. So additional categories of technical safety requirements. So one is detecting faults within the system. So the validity and the integrity of the data transmission shall be ensured. One is detecting faults in the external device interacting with the system. For example, the anti-lock brake ECU, the external system to the lane assistance item, might send vehicle speed information. So to ensure that the message transmission does not have faults, you can add cyclic redundancy checks or live counters to detect faults in the data transmission. And reaching a safe state. For example, as soon as a failure is detected, it shall deactivate LDW and set the torque request to 0. Number 4 is implementing a warning and degradation concept. So as soon as the LDW is disabled, the LDW safety software block shall send a signal to the car display ECU to turn on the warning light to the driver. Number 5 is preventing latent faults. So memory tests should be conducted at startup of the EPS ECU to check for any faults in memory. So that's additional software component. So here's an example of technical safety requirement. So first, it inherits the ACL from the corresponding functional safety requirement. So 1 to 4 are based on the functional safety requirement. The lane keeping item shall ensure that the lane departure oscillating torque amplitude is below a threshold. Because that FSR is SOC, the 4 technical safety requirements are all SOC. And the requirement number 5, the memory test requirement, is SOA, since latent fault detection for SOC requirement can be labeled SOA. So this is a latent fault detection. Therefore, it has a lower ASIL than the other technical safety requirements. And also, you have the FTDI requirement. fault tolerance time interval. So after you have identified the technical safety requirements, the next step is to allocate the requirements to system architecture. So 1 to 5 have been allocated to different software elements, such as the LDW safety functionality, block, the data transmission, integrity check block, or other relevant blocks. So for the SOC requirements, when they are mapped to the software component, software blocks, then these functionalities get SOC. For the SOA requirement, is mapped to the memory test block in system safety startup software. Then it's mapped to SOA. So notable points, elements inherit the highest ASIL from the technical safety requirements. So if the same software element provides a functionality to SOC and SOB functions, the higher ASIL wins. So this software element is assigned SOC. So if an element contains sub-elements with different ASILs, then the both sub-elements will receive the highest ASIL, with some exceptions. So if a failure in one sub-element will not affect the other sub-element, then the sub-elements can have different ASILs. So internal and external interfaces needs to be clearly defined. Finally, we have functional safety for hardware and software. So this is at even lower level after so much requirements engineering at the functional requirements and the technical requirements. Now we are ready to actually develop the hardware and software. So now we have two little V cycles. If you remember from the document we saw before, you have a larger V cycle and two smaller ones, one for hardware development, one for software development. So for hardware, the V model includes sections about hardware architecture metrics and evaluation of random hardware failures. For software, there's an architecture design section as well as a unit design section. So a unit is a smaller part of a software architecture. For example, it could be a software driver to read raw data from a camera sensor. So from a bird's eye view, at a high level, you can see the shapes, the steps of the V model stretched out vertically. So you start from the initial technical safety requirements, and then you map to different subsystems, subsystems A and B. And in subsystem B, you may further decompose it into B1 and B2. And in each of the subsystems, at the leaf level, you will perform actual product development at hardware level and software level. And integration and testing with hardware and software. And finally, you perform a system integration and testing. So programming languages popular in the automotive industry is C and C++ and MATLAB. MATLAB is the de facto standard for control software design. So it has automatic code generation to C and C++. So Measure C is a standard for safety critical applications, which defines defensive implementation techniques to prevent unsafe operations, language subsets, style guides, naming conventions, and so on. So if you're a programmer in the automotive industry, you're likely to have to respect this standard. So software safety requirements are derived from technical safety requirements. So from one technical safety requirement, you may have multiple software safety requirements. And in the product software architecture, you may have different safety software blocks that actually implement the software safety requirements. So here's the freedom from interference. This ensures that a failure in one software element does not spread and cause failure in other software elements that communicate with it. So the interferences include spatial or temporal. So maybe between software elements with the same ASIL or different ASILs. So here's freedom from interference between one ECU with ASIL-B elements and another ECU with ASIL-B, or one ECU with ASILs C and B components elements, another ECU with ASIL A and D elements. So you should ensure non-interference among the different ECUs. So spatial interference is when memory address spaces of software elements shall be partitioned and not interfere with each other. So here shows a counterexample. A QM software element has a bug that creates a pointer to the memory address space of a software element accessed by ASIL-C element. So, and writes to it, leading to a safety goal violation because it violates the non-interference requirement. Temporal interference, so the top shows a blocking of execution due to shared data. So here, software element here and this element share the same data. Therefore, when this element is executing, lower priority thread is executing, it blocks execution of the higher priority thread due to the mutual exclusion. And in the middle, you may have a deadlock situation. So software element A is holding resource A and requesting resource B. And software element B is holding resource B and requesting resource A. And then you have a classic deadlock scenario. In the bottom, you may have incorrect sensor fusion due to incorrect clock synchronization between software elements. So suppose you want to perform sensor fusion between radar and camera. And you need to have accurate timestamps on the data received from the two sensors. So if you have incorrect clock synchronization, you may wrongly associate the two sensors at different time instants. Therefore, the sensor fusion will be wrong. So more examples of temporal interference. So incorrect allocation of execution time and incorrect execution of sequence. So for the top example, you see a live supervision checks number of times a software element is executed in a time span. So here we check for the correct execution is 3 times in the time interval. And incorrect execution number 1 has only 2 executions. It's not frequent enough. And the next one executes too frequently with 4 executions. Both are incorrect. In the middle, you have deadline monitoring to check if a software element is executed before its deadline. So a correct execution is when software task finishes before deadline, and incorrect execution is when it exceeds the deadline. Control flow monitoring checks software elements are executed in the correct sequence. So correct execution is A, B, C, D, whereas incorrect execution is A, Z, or B, C, D. So these are all examples of temporal interference. And communication interference and end-to-end protocol. So this concerns communication channels between ECUs with different, because the communication channel is often QM. So data transmission errors on the channel are possible because the buses are very difficult to certify. So you cannot really ensure error-free transmission. Usually you leave them as QM and implement higher level protocols to ensure reliability. So end-to-end protocol can be used to detect errors due to transmission errors, for example, with CRCs. So here's the example of 2 ECUs communicating via QM communication channel, which may corrupt the data. So you may perform CRC check or other end-to-end checks to detect the error at an ECU level. So here's a software architecture safety design pattern called EGAS. So EGAS is a standard in the German automotive industry. So it's at a pretty low level in the system stack. So here's a basic idea. You have a level 1 normal system functionality. Then you implement multiple levels of monitoring. Level 2 monitors level 1 for safety goal violations, called functional monitoring. And level 3 monitors level 2 for processor monitoring, monitors hardware for any possible faults. So for example, if level 2 monitoring detects a safety goal violation, output from level 1 is disabled, and level 2 software leads the system to a safe state by setting torque to 0. Okay, so that's the end of the functional safety chapter. So I went through this chapter pretty quickly. Any questions?
Hi.
Yeah, yes?
I don't have a question regarding the specific slide, but I just wanted to know that you have linked many other YouTube slides regarding to the functional safety requirements. I was just curious, like we have to go through all of them, or just your lecture is enough for the exam? Yeah, can you please clarify this thing?
Yeah, so anything I put in the additional reading section are optional. So only required reading is my PowerPoint slides and my lectures.
Okay.
Yeah, so for the functional safety,
Yes.
the tutorials are incomplete. They only pull out 3. I think more are coming. The others are, some are full courses. I wouldn't expect you to go through all of them. It'll take you forever. So yeah, all of these links on the right are optional.
Oh, okay. Okay. Yeah.
For the particular lesson today, I think what's likely to be covered in the exam is the Acl determination. So I may give you a scenario and let you determine the severity, exposure, controllability, and check the table for Acl level for it. For the others, I think it's pretty much just knowledge that's difficult to give any questions about. Yeah, as long as you understand this table, things should be okay for the chapter.
Okay, thank you so much.
Yeah. Yeah, so the next lecture is on next Wednesday because Monday is the POSC. So on Wednesday, we'll discuss Introduction to Machine Learning. The PowerPoint slides is not ready yet, but I'll upload it in the next few days. Okay, so have a good POSC and see you next week.
Bye.
Goodbye.